Hello friends, I welcome you in lecture number 10 on recurrence relations. In this lecture, we are going to solve one recurrence relation which is non-homogeneous, and we will apply the method of undetermined coefficients to find out the solution of given recurrence relation together with initial condition. We have discussed about method of undetermined coefficients for the solution of non-homogeneous recurrence relations in lecture number 9. So if you have not seen lecture number 9, then I suggest you to watch that lecture first before going for this lecture. In this lecture, we are going to apply method of undetermined coefficients to solve this recurrence relation, which is non-homogeneous linear recurrence relation with constant coefficients. And after solving this recurrence relation, we have to find out particular solution satisfying this initial condition a1 equal to 3. The same question can be asked in this way also. Solve the recurrence relation an equal to 3 times an minus 1 plus 2n with a1 equal to 3 using the method of undetermined coefficients. Now, to solve the non-homogeneous recurrence relation, first step is to write down the homogeneous recurrence relation associated with given non-homogeneous recurrence relation. So for that homogeneous recurrence relation, we ignore the function of n which depends on n only. Here f of n is 2n, and this f of n makes this recurrence relation non-homogeneous. So we ignore this term and we write down the corresponding homogeneous recurrence relation, which is an equal to 3 times an minus 1. This is the associated homogeneous recurrence relation to given recurrence relation, and we find out general solution of this recurrence relation, and that we will denote by this notation ANH. So first I have obtained the solution of associated homogeneous recurrence relation an equal to 3 times an minus 1. First I have rewritten in this form. I transfer this on left hand side and I have an minus 3 an minus 1 equal to 0. Now to solve this homogeneous recurrence relation, we have to consider the solution in this form an equal to r raised to n, and we replace an by r raised to n here. So we have an equal to r raised to n minus 3 times, if an is r raised to n, an minus 1 is r raised to n minus 1 equal to 0. And if we take r raised to n common, or if we consider r raised to n minus 1 common, then here we are left with r and minus 3 equal to 0. And in the next step we will have r minus 3 equal to 0, and that is the characteristic equation of this recurrence relation. So to write down the characteristic equation, we will replace an by r raised to n, and after that we will replace n by degree of recurrence relation. This recurrence relation is of first degree, so first we replace an by r raised to n and then n by 1. So we can directly write in this way also. An is replaced by r minus 3, an minus 1 is replaced by r raised to n minus 1, and n is replaced by 1, that is r raised to 0, which is 1. So we have r minus 3 equal to 0. And if you are not comfortable in this way, then you can put an equal to r raised to n, an minus 1 equal to r raised to n minus 1, and then take the lowest degree term common or divide by lowest degree term, and you will obtain the characteristic equation. So the characteristic equation is r minus 3 equal to 0. Therefore r equal to 3. There is only one root of the characteristic equation, because this is recurrence relation of first degree, and therefore the general solution of this homogeneous recurrence relation is alpha times r raised to n, and r is 3 here, that is alpha times 3 raised to n, and that we denote by anh. This is the first step. Whenever you want to solve any non-homogeneous recurrence relation, first you write down the associated homogeneous linear recurrence relation and then find its general solution and denote that general solution by this symbol anh. H stands for homogeneous. Now in the next step we will concentrate on the function f of n, which makes our recurrence relation non-homogeneous. Here f of n is 2n. Let me write here f of n is 2n. So first we have to decide the form of particular solution, and that form of particular solution depends on the function f of n. Now as we have discussed in lecture number 9, first we will write our function as the product of polynomial and nth power of some constant, say s raised to n. So here we can see I have polynomial of first degree or polynomial of degree 1, and there is no s raised to n multiplied here, so I can consider s equal to 1. So I have product of polynomial of first degree and s is 1. Now after that I will check whether this value of s is a root of characteristic equation or not. Here root of characteristic equation is only 1 and it is s equal to 3. It is r equal to 3. Here I have written that r minus 3 equal to 0. So r equal to 3 is the only root of characteristic equation. So that means s equal to 1 is not a root of characteristic equation. Therefore what we will do, we will write down the arbitrary polynomial of first degree, that is p0 plus p1n, and this 1 raised to n as it is, and 1 raised to n is 1. Therefore our choice for a particular solution is p0 plus p1n, where p0 and p1 are real numbers or constants or coefficients to be determined. So in this way we can write down the form of particular solution. I have written here f of n is 2n, that I have written as 2n times 1 raised to n, and 1 is not a root of characteristic equation of 2, that is homogeneous recurrence relation. Therefore there is a particular solution of given recurrence relation of the form an equal to p0 plus p1n into 1 raised to n. I have written polynomial of first degree because this is polynomial of first degree, and 1 raised to n is 1. Therefore this is our trial solution for given non-homogeneous recurrence relation. Now I have to decide p0 and p1, and I will use this notation a and p for particular solution, and final solution will be addition of anh and anp. So you must write a and p, that is particular solution. Now once we assume that this is a particular solution of given non-homogeneous recurrence relation, it will satisfy given non-homogeneous recurrence relation. So in the next step we write that since a and p is a solution of given non-homogeneous recurrence relation, we can replace an by anp in the given non-homogeneous recurrence relation, because now we have assumed that a and p is a particular solution of this recurrence relation. Therefore we can substitute an or we can replace an by anp. So I will have anp equal to 3 times an minus 1p plus 2n. So that I am writing here. a n p equal to 3 times a n minus 1 p plus 2n. Now I put value of a and p. It is p0 plus p1 into n plus 3. Here I have a n minus 1. If a n p is p0 plus p1 n, then a n minus 1 p will be p0 plus p1 into, instead of n I have to write n minus 1 and plus 2n. Now I simplify this. This is p0 plus p1 into n, and let me write one more step. This I can rewrite as p0 plus p1 into n minus p1, multiply this bracket by p1 and plus 2n. Therefore p0 plus p1 into n equal to 3 times p0 plus 3 times p1 into n minus 3 times p1 plus 2n. And let me transfer all these terms on left hand side. So you can see p0 minus 3p0, that is minus 2 times p0, plus I can take p1n, or let me write one more step, p1n minus 3p1 into n plus 3p1 equal to 2n. And this I can rewrite as minus 2p0. I combine this term which is independent of n. So minus 2p0 and 3p1 are independent of n, plus here if I take n common, I will have p1 minus 3p1. So p1 minus 3p1 into n, and that is going to be minus 2p1 into n equal to 2n. Therefore minus 2 times p0 plus 3 times p1, and this is going to be minus 2p1 times n equal to 0 plus 2 times n. Now we compare coefficients of equal powers of n on both sides, or we can see this is a polynomial of first degree and this is also polynomial of first degree. Therefore these two are equal if we must have their coefficients are equal. Minus 2p0 plus 3p1, which is constant term here, and on the right hand side constant term is 0, and here coefficient of n is minus 2p1, here it is 2. So here I will obtain p1 equal to minus 1, and if I substitute p1 equal to minus 1 here, I will have minus 2p0 plus 3 into minus 1 equal to 0. Therefore 2 times p0 minus 3 equal to 0. Therefore this is minus 2p0. So therefore minus 2p0 equal to 3. Therefore p0 equal to minus 3 by 2. So we have obtained values of p0 and p1, and both are negative. So now we can put these values in this trial solution. We have obtained this p0 and p1. So our particular solution is, therefore a and p equal to p0 is minus 3 by 2 plus p1 into n, p1 is minus 1. So this is the particular solution of given non-homogeneous recurrence relation. In the next step we will write down general solution by adding a n h and a n p. The general solution of given recurrence relation 1 is a n equal to ANH plus ANP, and therefore AN equal to ANH was alpha into 3 raised to n, and here I have minus 3 by 2 minus n. Let me check ANH also. ANH is alpha times 3 raised to n. So this is the solution, or all these are, this is the set of all possible solutions. If we start with n equal to 0, 1, 2 and so on, then this expression gives all possible solutions of the given non-homogeneous recurrence relation. Now we are given one initial condition also, so now we use that initial condition and we obtain the solution satisfying that initial condition. Initial condition is a1 equal to 3. So for a1 we put n equal to 1 in this solution. Taking n equal to 1, we have a1 equal to 3 into alpha. For n equal to 1 we have 3 here, minus 3 by 2 minus 1, and therefore it is given that what is a1? A1 is given to be 3. So I put a1 equal to 3, and after solving this I will obtain value of alpha. This is 3 alpha, and this is going to be minus 3 minus 2 minus 5 by 2. I am interested in the value of alpha, so that is 3 plus 5 by 2, and this is 6 plus 5, that is 11 by 2. Therefore alpha is 11 by 6, and I will substitute this value of alpha here and I will obtain the particular solution. Therefore the solution of given recurrence relation satisfying given initial condition, or satisfying a1 equal to 3, is, here I have to put alpha equal to 11 by 6. 11 by 6 into 3 raised to n, 11 by 6 into 3 raised to n, and minus 3 by 2 minus n, minus 3 by 2 minus n, and this is the solution satisfying given recurrence relation as well as given initial condition. We can cross verify our answer. We can put n equal to 1 and we can see whether we obtain a1 equal to 3 or not. This is minus 3 by 2 minus 1, here 3 and 2, so I have 11 minus 3, that is 8 by 2, and minus 1, that is 4 minus 1, which is equal to 3. Therefore this is the solution satisfying the initial condition a1 equal to 3. This is just for cross check. You don't have to mention this verification in your examination. So this is fine. It is the particular solution satisfying a1 equal to 3 as well as given recurrence relation, and this includes all solutions of the given non-homogeneous recurrence relation where alpha is arbitrary constant. For different values of alpha we will have different solutions to the given recurrence relation. Therefore this expression is in general, and therefore it is known as general solution of given recurrence relation. The main thing in this method is the correct choice for particular solution. Whatever trial solution we are assuming, if there is mistake in the choice of that particular solution, then we will get our answer as wrong. So the main thing is how to select appropriate particular solution, and for that we have explained the method of undetermined coefficients in lecture number 9. what we have to remember is visualize our function f of n as the product of polynomial and nth power of some constant, say s raised to n. Then check whether this s is a root of characteristic equation or not. If s is not a root of characteristic equation, then write down arbitrary polynomial into s raised to n as your choice for particular solution. And if s is a root of characteristic equation with multiplicity m, then multiply this choice by n raised to m and modify your particular solution. So remember this part only, and whenever your right hand side is in this form, you can apply this method. So this is all about this session. I hope you like it. Thanks for watching.